Hello everyone and welcome. Welcome to our summer school workshop, Quantum Horizons, Developments and Opportunities, where we will have another exciting session with Professor Menno Poot from Technical University of Munich, as well as from Munich Quantum Center, a world-class expert in the field and a wonderful person and a friend. He is also an associate member of TÜBİTAK Research Institute for Fundamental Sciences, which is a pleasure and honor for us. Menno Poot is a Rudolf Moesbayer professor at the physics department of Technical University of Munich, where he leads a research group which focuses on quantum technologies. His research interests include studying the dynamics of nano-mechanical resonators at extremely low temperatures, just a few thousand of a degree above absolute zero. At such temperatures, resonators are in their quantum ground state, and their behavior can be probed using extremely sensitive optomechanical techniques. Professor Poot's research group also looks and integrated quantum optics. Professor Menno Poot has kindly agreed to join us for this school, and he's going to give a series of lectures under the title, The Ultimate Quantum Limits to Position Detections, what it takes to detect gravitational waves. With this, I want to thank Professor Menno Poot once again for joining us and invite him to the stage to begin his talk. Menno, please come.
Okay, thanks a lot for this very kind and lengthy introduction. I feel really honored to be presenting here at this summer school. Of course, I would have loved to be to meet most of you in person, but I think this year we have to do it online. But maybe we see each other in the future in person. So, as already said, today I will talk about the ultimate quantum limits to position detection, and this is something that is coming from the context of quantum sensing. And in particular optomechanics. And then, of course, that is a very broad field with many different applications. And we will focusing today on one particular task, and that is, what does it take to detect gravitational waves? So that kind of is what my lecture will be about. So it will be kind of in three parts. We will combine the two parts into one with a short break in between, and then we have a lunch break, and then we have the final part of this lecture. So to get started, maybe you ask yourself, well, what is then optomechanics? Well, optomechanics is the field where people use light to measure and to alter the dynamics of a mechanical resonator. And a mechanical resonator can be almost anything, because they can range from these kilometer-long gravitational wave detectors that you see here at the top, and that we'll take a closer look at in an hour or so, all the way down to these nano-fabricated devices that you see here at the bottom. And when you look at the different length scales, the different masses and the different frequencies, you can see the trend that if you make the devices smaller, they get lighter, but also faster. For example, the gravitational wave detectors have kilogram mirrors that are swinging at hertz frequencies, whereas those nano-fabricated devices have femtogram masses and they're moving about 1 billion times per second. However, what all of these devices have in common is that their sensitivities is expressed in the units of femtometer per root hertz. And of course, this sounds a bit strange. What does this unit femtometer per square root hertz mean? Well, we're going to dive much more into that topic later on. But it basically means that if you give me 1 second to determine the position of any of these mechanical resonators, I can determine their position with an accuracy that is smaller than the size of the nucleus of an atom. So in other words, optomechanics allows us to measure extremely small displacements. That's of course great, because these displacements convey a lot of information. For example, we can drive the motion of these resonators and then see how the driven motion is impacted. For example, when there's mass added to these mechanical devices, or when you're scanning a mechanical cantilever over a surface, in other words, when you're doing atomic force microscopy. So that is if you drive these resonators yourself and then see what the effect of external influences on that motion is. You can also look at the intrinsic motion, that is, you look at thermal or quantum motion, or as we have also looked at in our research, to look at squeezed motion. But also you can see what the impact is of external forces. And in this context of this lecture, we will take a closer look at, towards the end, what happens when you have gravitational waves acting on mechanical devices. So this kind of gives you an overview of what optomechanics is, and I want to share with you that the lecture that I will be presenting today is kind of part of a course that I'm teaching here at TUM. It's called Nano Optomechanics, and there's a lot of very interesting stuff going on. So in this course, there are many different topics that will be covered, but this is a course that has about 50 hours of lectures, and today we only have 3 hours at our disposal. So unfortunately, we have to make a selection here. And as I said before, we are going to look at quantum limits on position detection and also gravitational wave detectors in a lot of detail. However, this is of course not possible without much of the background. So in this case, whenever we need to have background information, we'll also cover some of the topics that are here, but of course not in that much detail as we would cover it in the entire course. So that is what we will be looking at today. And during today's lecture, I will use the presentation as you see it now. We'll also have a short exercise where you can play a little bit around with numbers, get a good feeling for how large and small different quantities are. And also we use a screencast to derive the so-called House-Caves law for quantum limits. So now I can imagine that this lecture will get you really excited about the topic of optomechanics and quantum sensing with these kind of mechanical resonators in general. And therefore, there's also these two review articles that you can use for background reading. However, these are, of course, real research papers. So the level may be pretty high, but still, I think you can browse through them and see what interesting things are and how these are addressed, and also look up the more original research. So that kind of sets the stage. I also want to tell you that if you have any questions during the presentation where maybe you think something is unclear, then feel free to unmute yourself and to ask a question. I'll be more than happy to answer that. Of course, every time before we end one section, I'll also ask explicitly if there are questions, but feel free to speak up and ask questions if you want to clarify things at that point. Okay, so we have quite a bit of ground to cover. So we have, as I said, 3 different parts. One is the introductory part, where we have the introduction about today's course, and that is something that we have now already done. Next, I will tell a little bit more about TUM, about myself, and also the work that we do in our group. And then we dive into the science. That is, we're going to talk more about optomechanics, and also we'll take a closer look at some of the measurement equipment that is very often used in this case. And we'll focus on a device called the spectrum analyzer. Then in the second part, we are going to take a deep dive into the quantum limits. And some of these quantum limits may sound familiar. For example, when we talk about the Heisenberg uncertainty principle, but then we switch gears and go to the House-Caves in the so-called standard quantum limit. And then in the third part, we will discuss what it takes experimentally to detect gravitational waves. So that is kind of what we have on the program for today. So as you can see, the next thing is to tell a little bit about Technical University of Munich. So this is a picture of the campus. And actually, the TU Munich has many different campuses. So there are 6 different sites. And there is, of course, one in Munich, a very big one, the original one. And then I am sitting here in Garching, which is like 20 kilometers away from downtown Munich. And that is where the second largest campus is. In this case, there is the physics department, there's the chemistry, we have a nuclear reactor. So there's a lot of things going on here in Garching as well. So to give you an idea of how large TUM is, so we have about 600 professors. There are about 15 schools and departments, and we have about 10,000 students that graduate every year. So TUM is a relatively large university, and it's not only large, it is also considered a good university when you look at the rankings that are that are presented every year, and you can see that indeed we are leading both in Germany and also pretty good in terms of global competition. Also, TUM has been named a German University of Excellence for 3 times in a row. And of course, that is very nice, but it also means that there are many different clusters of excellence. Those are kind of topics that are being pursued within such an excellence cluster. And the particular one that I am involved in is the so-called Munich Center for Quantum Science and Technology, or MCQST for short. And in this case, there are 7 different research units that comprise all the different areas of quantum science and technology, ranging from basic research all the way to applications. And this is a joint effort between the other university in Munich, the Max Planck Institute for Quantum Optics, also here in Garching, and the Walter Meissner Institute for Low Temperature Research, and also the Deutsches Museum is involved in this. So now I hope you have gotten a little bit of a flavor of what kind of university TUM is. So let me now tell also a little bit about myself. So I did my undergraduate studies at TU Delft, starting in 2000. It's already a long time ago, but then I got my my bachelor 3 years after, then again 2 years in my master's, and I did that in applied physics. And after that, I stayed at TU Delft and did my PhD with Professor van der Zand, where I worked on mechanical systems at the nanoscale. Then after that, I moved to the United States, where I did a postdoctoral research with Professor Tang in the Department of Electrical Engineering of Yale University, where I started working on optomechanics and integrated quantum optics. And these are still the research teams that we pursue in our group at TUM. And I've been at TUM since 2017, where I lead the quantum technologies lab in the physics department. So, of course, in all of these places where I stayed, I did a lot of different things, also a lot of different experiments, but I want to give you a little bit of a flavor. So at TU Delft, I mainly focused on nano-electromechanical systems. And here you can see, for example, one of the devices where we made very thin drums where graphene, an atomically thin material, was suspended over holes, and by using an AFM tip, we could press against these little drums and measure the mechanical properties. And with that, we could also infer what the mechanical properties of these graphene flakes were. So that is something that we did already a little while ago. And then a few years after that, we also show that if you now use these kind of devices, they look a little bit different, but still suspended graphene drums, you can also use these to make optomechanical oscillators, where in this case, blue detuned light was used to create self-sustained oscillations of these atomically thin vibrating drums. So this is now something that is very, very thin, but still you can see these flakes. That is the gray thing that you see in the upper left corner is something that is 2-dimensional. We also studied 1-dimensional mechanical resonators, and in this case, that was done using carbon nanotubes, which is now a nanotube that is maybe a few micrometers long, but actually it is just a few nanometers thin. So it is extremely, extremely narrow in 2 dimensions and then long in the 3rd dimensions. In other words, this acts as a string, and we cool these strings down to very low temperatures, to millikelvin temperatures. And then there is the interplay between electrons that are tunneling through these carbon nanotubes. Those electrons, they tunnel one by one, and we can actually see that if we look at the measurement that we have over here, and every time when electrons can tunnel on and off the device, you see a very deep dip in the resonance frequency of this mechanical device. And every time when you go to an average occupation that differs by 1, you see a step. So in this case, we could really show that you could measure the effect of a single electron on a mechanical resonator. So these are electromechanical devices. We also studied a different type, namely so-called superconductor quantum interference device, or SQUID, where in this case there was a mechanical resonator embedded in the superconducting loop, that is the brown thing over here, and also that we could use to very sensitively measure the displacement of the mechanical resonator that was incorporated in this SQUID loop. So in this case, you see there's always electrical wires, current flowing, where there's normal currents from electrons or supercurrents in this device. But then a little bit later, during my postdoc, I started to do optomechanics. And in this case, we started, for example, large amplitude motion and synchronization between multiple resonators using light, but also a little bit more applied things, such as nano-optomechanical devices inside microfluidics. In other words, things that you can use for very sensitive sensors, but also then things like cascaded electromagnetically induced transparency, or to shift the frequency of single photons using optomechanical devices, as you can see over here. But when you think about that, then of course it probably comes as no surprise that what we are continuing here at TUM is also to combine now electromechanics with optomechanics. And the idea is that for optomechanics, you have very good sensitivity, and that's because you have very low noise lasers, and you can also detect photons coming from your device with a quantum limited precision. But the problem there is that the photons in generally interact only very weakly with the resonator, and we'll see that the momentum of a single photon is about 4⁻⁻28 in SI units. So in other words, every time when you send photons into this optical cavity, they will bounce off this mirror and impart twice the momentum to this mirror, but this momentum is tiny. So on the other hand, we have nano-electromechanics, and in this case, the sensitivity is relatively low, at least compared to optomechanics, unless you use these special mesoscopic devices, such as the squid that I showed you before. But the nice thing here is that you can have very strong electrostatic forces, and these forces are typically inversely proportional to the gap. So for example, here you see a cartoon of a carbon nanotube suspended above a gate electrode, and the smaller you make the distance between them, the stronger the force is. And that is why we typically want to study nano-electromechanics compared to the much larger micro-electromechanical devices. So also at TUM, we of course have been working for quite a while now on combining optomechanics with electromechanics. And here you can see an example, more technological oriented. This is what we call an optomechanically tunable directional coupler. And the idea is that we can send light through grating couplers onto these devices, and then the light will travel through the waveguides that you can see, and it comes out on this side, also on this side. But when we now zoom into the mechanically active region, then you can see there's the structure over here, where the light actually travels very close to these two waveguides, and part of the light will travel from one waveguide into the other, thereby crossing over, and part of the light will go through. And how much light crosses over and goes through is something we can control mechanically. By applying voltages between the electrodes, we can displace the mechanical resonator, and then we can see that we can tune how much power is going into one of the outputs and how much goes to the other outputs. And you can see that we can use now the voltage to tune these directional couplers to be exactly 50-50 beam splitters, things that we need for our integrated quantum optics circuits. So in this case, the tunability was relatively small, but good enough to really trim these devices towards a 50-50 beam splitter. We can also have different device geometries that now show you much more, and you can use this now as a switch where you can route the photons onto the chip. So this is something that we use both for optomechanics, but also for integrated quantum optics. We also do a little bit more pure optomechanics, to be honest. And in this case, we have these kind of devices. So these are silicon nitride strings, but you can see they have this wavy displacement. So we use this this pre-displacement of the strings, which have a lot of tension in them, to actually geometrically tune the stress in these kind of string resonators. And the idea is now that you can fabricate them or make them with this design. There's a lot of stress into this, and just like a rubber band that is stretched, you will see that if you now release these mechanical devices, they will relax slightly, and thereby you can see they have less displacement than they originally had in this case. And then we can analyze in detail, theoretically, what goes on. And this would be a picture of the potential for these kind of pre-displaced resonators. And you can see that when you design them with a pre-displacement of 4.5 micrometer, that's the position of the white cross. Then when you release them, they will go towards the minimum and actually find that there is a certain relaxation, and that is something that then reduces the tension, and you can use that to really geometrically tune this the stress in these devices. So this is a device where you can also again see a waveguide. So these are on-chip devices. We also do free space optics. Here you can see now a zoom of a microscope objective, a vacuum chamber, and then the black thing inside here, that's one of our chips. And now we can do optomechanics from the top side. So in this case, we see, for example, a cantilever that we are combining with transition metal dichalcogonites, also two-dimensional materials. We can study waveguides made of repeating elements and look at defects and molecule things that we can build in there. And you can see we can measure very nicely the different resonances through these kind of things. And also quite recently, we developed a method that we can use to map images of modes of these kind of square and also rectangular membranes. And you can see very nicely here the image of the two modes. So these are a few of the examples of the work what we do. But of course, we are not here to learn so much about that, but we want to know what it takes to detect gravitational waves, right? So now let's switch gears and go to the actual scientific part of this lecture. So in the first question, what is optomechanics? I already tried to answer, but when you look at the name optomechanics, you see it contains two parts, namely an optical part and a mechanical part. And for the optical part, we usually use an optical cavity. And the prototypical case is shown over here, where we have two mirrors, and this forms a so-called Fabry-Perot cavity, where in this case, when we now use a laser, we can send light onto those two mirrors, and part of the light will go into the cavity, as you can see over here. And in this case, the light will bounce back and forth between those two mirrors, and then it can again escape through this mirror over here, or part of the light can actually go out on the other side to the other mirror. So in this case, we can place a detector over there, and now you can see, sorry, that in this case, the detector is not measuring much light. You can very faintly see there's some light in this cartoon going through, but it's hardly anything, and you can see that the detector, if you hook it up to a measurement device, gives a very small signal. That's because in this case, the laser light is not fitting into the cavity. So there's the resonance condition that an integer number of wavelengths should fit in this full round trip when light moves between the two mirrors. And that is not satisfied in this case. But when we now change the wavelength of the laser, you can see that at some point, there is actually a lot of light fitting in there when the light is kind of green in this cartoon. When that happens, then you can see there's a lot of light in there, and you also have a larger signal coming out of your detector. So that is a prototypical example of an optical cavity. Well, what about the second part of optomechanics? We also need some mechanics. So we need to have something that is moving in this picture. And again, the easiest system to understand is to make one of these mirrors movable. So now we have this second mirror, this end mirror, and we attach it to springs, and that is then fixed to the fixed world. So now we have a movable mirror, and then when we drive this mirror, when we give it a kick, when it starts to oscillate, then in this case, you can see that the length of the cavity is changing. And even although now the wavelength of the laser light that we use is fixed, you can see that when the mirror is moving, actually you have fulfilled the resonance condition at some instance in time and not at other instances in time. So in other words, you can see now in the picture that as a function of time, the amount of light that falls into the detector is changing, and that allows us now to measure very sensitively the position of the movable mirror by looking at the signal that is detected, as we see in this animation. So in this case, we see that optomechanics has this very good sensitivity, and this is now kind of the prototypical example of the optomechanical system that we will look at. So in the introductory slide, I showed you there are many different types of implementations of these optomechanical devices. But for easiness of understanding, we will mainly focus on the simple example where we have two mirrors, one which is fixed, one which is is movable, and then we send light into this Fabry cavity. The light will enter through this mirror over here, which is not perfectly reflecting, but has something like a 99.9% reflectivity. So 0.1% of the light can go through. And when the light enters this cavity, it can bounce back and forth many, many times, interact with the mechanical resonator. Although that interaction of a single photon is pretty small, of course, you can always put more photons in there and have these photons bounce back and forth many times. And that way you can kind of increase the momentum of this, or the impact of a single photon onto this mechanical resonator. And at some point, the photon will again leave the cavity either through the same path at which it enters, or as we saw in the double-sided cavity on the previous slide, it can also go to the come out on the other side. So this is now the prototypical example, and we have seen that there are now many different types of implementations, and that also includes many different types of mechanical resonators. So maybe you're wondering, how should we model this? Well, it turns out that you can show that the eigenmodes of all those different mechanically active structures, whether it is complicated as these directional couplers that I showed you earlier, where you have different arms, you have a photonic crystal in here, you have these waveguides that are close to each other. So you can have many different complicated eigenmodes for such a mechanical structure. But it turns out that you can actually map all of these eigenmodes onto a single harmonic oscillator. So in other words, we can have very complicated mechanical devices, but if we then focus on a single eigenmode of this structure, we can map that directly onto a simple harmonic oscillator, as you can see here, that could be modeled by a ball on a spring or a marble rolling in the quadratic potential. So that's of course a great simplification, because without that we would have to do a lot of work to understand the dynamics of all these devices. But now we know that once we find the eigenmodes, you can do that analytically for certain cases. You can also use, for example, finite element simulations for these more complex devices, as you can see. But once we find the eigenmodes, we can see that the behavior of these eigenmodes is completely described by the harmonic oscillator. And I hope you remember that the equation of motion for the harmonic oscillator is given by this, this thing over here, where you can see the acceleration of the displacement is given by the restoring force, where in this case the restoring force is written as m omega 0 squared, where omega 0 is the angular resonance frequency. So when we divide it by 2 pi, we get the actual resonance frequency in hertz. And this combination of m omega 0 squared is the spring constant that we usually label with k. And then we also see there's a term that depends on the velocity, and that is giving rise to dissipation. So in this case, the term gamma is the so-called damping rate. It tells us how quickly the energy is lost once we put it into our harmonic oscillator. And then finally, you see this term F all the way on the right, and that is the force that is acting on the mechanical resonator. So this is something that you've probably seen before. But what you may not have realized is that this equation of motion for a harmonic oscillator can also be viewed as a so-called linear time invariant system. And in this case, these linear time invariant systems mean that you have a black box where you have an input and an output. And in our case, we have the black box, that is the harmonic oscillator. It is described using this equation of motion. And then the input of this this linear time invariant system is the force. That is what is going to drive our harmonic oscillator, our mechanical system. And then in the end, we're going to get the displacement. And this displacement we usually indicate with the symbol U. In case you're wondering why not X, well, that's because we also have to work often with structures that actually are more complicated, where in this case we use X, Y, and Z to describe the coordinates where we are in our, say, complicated resonator, and we use the displacement U to actually indicate what the displacement is at that position. Of course, that's just notation, but the important thing is that we can view these harmonic oscillators as a linear time invariant system. And in case you're wondering, what does it mean? Well, it first means it's linear. That is, if we apply a force that's twice as large, then the displacement that we're going to get is also going to be twice as large. If we apply the sum of two forces, then the displacement that we're going to get is also the sum of the displacement that you would get when you would apply the forces one by one. So that's the linearity. And the time invariant part means that if we apply a certain force today, I'm going to get a certain displacement today. And if I apply the same force tomorrow, I'm going to get exactly the same displacement as today, but then I'm going to get it tomorrow. So that means that there's no internal clock in this black box here that gives a time dependence. So these harmonic oscillators can be viewed as linear time invariant systems. And then when you look at the theory of these systems, there's a lot of work done in that case. Then in this case, when you want to analyze the dynamics of these linear time invariant systems in a time domain, you want to use the impulse response or the Green's function, because you can then use convolution to find the output for any given input. And in this case, that uses this impulse response in h of t. And this impulse response function is nothing but the displacement that you get when you take your harmonic oscillator, give it a kick, and see how it oscillates back and forth many times, but ultimately the energy will be lost due to the dissipation, and that is what we see over here. So this impulse response function is nothing but taking the harmonic oscillator, give it a kick, and see how it oscillates back and forth and slowly relaxes. And once you have this impulse response function, you can calculate the displacement for any given force f of t using the convolution that you see on this little post-it note down here. So for example, if I take a crazy looking force as a function of time over here, and we want to calculate what is now the displacement if I would apply this force, then all we have to do is now convolute this force with the impulse response that I showed on the previous slide, and then we evaluate that integral that you can see over here. So it may be a little bit of work to do that analytically, but with a computer, very easy to do, and then this would be the resulting displacement. And that's, of course, very difficult to have obtained in any other way. However, as you can see, this is kind of a very artificial example. And in most cases, this is not the type of forces that we want to apply. So most of the time, we actually apply just a single frequency or maybe a few frequencies. And in that case, it's easier to work in the so-called frequency domain, where in this case, the force that we apply is, say, cosine as a function of time with a certain frequency, angular frequency omega, and also with a certain amplitude. And then what you're going to get is after a little while, you reach a steady state, the transients have died out, and in this case, the displacement that you are going to get is again sinusoidal. In this case, it also has an amplitude u0, it has a cosine of omega t, but in this case, there will also be this phase phi. So in this case, you see that the force and the displacement have a phase difference. And in this case, the thing that relates the input and the output to each other is the so-called frequency response. Again, we use the symbol h for that, but in this case, the upper case h, and we now have that as a function of omega, and it's basically telling us what is the amplitude of the output for a given amplitude of the input, and also we have to take the phase into account. So how would you now get this this frequency response? Well, it turns out that the fastest way would be to look back at the equation of motion that we see on the second line, take the Fourier transform of both sides, and then you will be able to find very quickly what the frequency response is. And then when you do that, you'll find this expression for the frequency response. You can see it contains the spring constant, it contains the frequency at which we're driving it, contains the resonance frequency, and also some other thing called the Q. So what does it now mean? So in this case, we see that the frequency response is the ratio between the displacement that you get at a frequency divided by the excitation at the same frequency. That basically means that the absolute value is given as the magnitude of the response. In other words, how many meters of displacement are we going to get per Newton of force that we apply? Although, of course, when we talk about nanomechanical devices, probably you're going to get something in picometers or nanometers or femtometers even per nanonewton, piconewton, or femtonewton. So in that case, these units will be a lot smaller, but still the absolute value of the response function gives us the magnitude of the response. And when we do that, we see this response function is a complex function. Here's an I. So we have to take the absolute value. You can do that. And then in this case, you get this formula here. And I don't know what you think of this formula, but I think it looks pretty complicated. So we can also plot it. And in this case, you see this is what it looks like. This is the response, the absolute value of it. And in this case, we see a clear peak at the resonance frequency. That's of course not so surprising. If you drive a mechanical resonator at its resonance, you're going to get a larger response than if you drive it off resonance. And this peak, as I said, is at the resonance frequency omega0, and it also has a certain width. And this width is determined by the damping rate gamma. And you can also see it has a certain height, and in this case, the height is given by Q. And Q is actually the ratio between the resonance frequency and the damping rate, and it's also called the quality factor. And the meaning of this quality factor is it counts how many oscillations there are before the resonator relaxes if you look back in this response function in the time domain. So in this case, you can see there are about 10 oscillations over here before they relax to a value of 1 over E of the maximum that they had. And you can see that was for a simulation for Q is equal to 10. If you have higher quality factors, usually we want to have very high quality factors, then of course you're going to have many more oscillations. This peak will be higher and it will also be narrower over here. So that is if we look at the absolute value, but if we again look at this response function, as I said, it is complex, so there's also a phase associated, and the argument of response function is actually related to this phase difference between the displacement and the force that we applied. And again, we can calculate what it is. You can see it is again a function that depends on omega, omega0 and Q, and it is again very complicated. So what does it look like? Well, it looks something like this. So you can see that in this case, at the resonance frequency, we have a phase of minus pi over 2. Far below the resonance frequency is 0, and far above it is minus pi. And this phase actually also has a physical meaning. So in this case, the phase tells us that there is a delay between the applied force and the resulting displacement. So in this case, when we now plot as a function of time the force that we want to apply, you can see the nice sinusoidal oscillations. And then if we are applying this force far below the resonance frequency, say at this frequency over here, then of course we know we're not going to get a large displacement. No, it's typically relatively small if you are far below the resonance frequency. But in this case, you can see that the oscillations in the displacement are really in phase with the force that we apply. And that is indicated by this phase that is now very close to 0. If we go to the resonance frequency, then there is this phase of minus pi over 2 or minus 90 degrees, if you prefer degrees above radians. And in this case, of course, on resonance, the oscillations are larger. But what you also see is that there is now a phase difference between the maxima in the applied force and those in the displacement. So you have to wait a little longer before you have gotten the maximum in the displacement compared to that in the force that you applied. And then if you go to even higher frequencies, that is above the resonance frequency, then in this case, you can see you again get a smaller displacement, but also that now you have to wait even longer before you can see this maximum appear. So in this case, this phase of the response function tells us the delay between the applied force and the resulting displacement. So this is now kind of the basics about the harmonic oscillator. I'm pretty sure some of this you already knew, but I hope there was also something new that you could take away from these few slides. So let me now switch gears and not talk about theory of harmonic oscillators, but now take an experimental point of view. So what we're now going to look at are measurement devices. So in this case, you see a measurement setup used by the group of in Yale by Jack Harris and co-workers. And in this case, they had a mechanical device inside a dilution refrigerator. It will be down here. And in this case, this measurement was used to study properties of liquid helium at very low temperatures. So I'm not going to go too much into the detail, and I'm also not going to explain every little element that we see here on the slide. But you can see that these measurement systems can be rather complicated with lots of different components that you have in there and lots of different measurement devices. However, when you talk about optomechanical devices, almost always you have a laser that you use for this. And of course, when you work with light, you also want to detect the light. So in this case, there are also photo detectors that we see here. And then there are a lot of devices to change, for example, the polarization, to modulate things, and also mixes and lots of complicated things, as you can see. But there's also these things here more at the bottom, where you can see there is a spectrum analyzer, there's a network analyzer, and also a lock-in amplifier. So this is now a schematic of a typical measurement setup for an optomechanical device. When we now look back in the lab where I was at TU Delft, then in this case there was this experiment with a squid that I told you earlier about. And then in this case you can see the dewar, and if you would be able to look inside, you would see the squid sitting somewhere in there at its millikelvin temperature. But there's also a lot of other things going on, such as the gas handling system to operate a dilution refrigerator, battery-fed electronics for low noise measurements. But then you also see here a stack of devices that are mains-fed. And in this case, when you will take a closer look, you will see lock-in amplifiers, oscilloscopes, spectrum analyzer, and network analyzer. So you see that a lot of the devices that we saw in the previous slide are also used in a completely different electromechanical system. And that means that these measurement devices that you use in opto and electromechanics are coming back over and over again. And I already told you, when you do optomechanics, there's hardly any way to avoid using lasers. And you want to detect the light, and you use that, do that using a photo detector. Then once you have that, you convert light into an electrical signal, and typically you want to amplify that. But then after you've done all of that, then you want to see your signal. And if you want to look at the signal in time domain, then you can use an oscilloscope. If you have want to measure, for example, the frequency response, as we discussed it earlier for the harmonic oscillator, then in this case you need to excite it at a certain frequency and measure what is the displacement at the same frequency, and that is something that you can do using a network analyzer. And then if you want to see what kind of frequency components are present in the signal, you use a so-called spectrum analyzer. So these are the measurement devices that come back over and over again when we talk about electromechanics, whether we talk about optomechanics, and so on. However, of course, we don't have time to go into the details of all of these, but we have already talked about the very good sensitivity of optomechanics. And from discussion, I hope it is clear that the sensitivity with which you can measure the position is somehow related to noise. And to analyze noise, the spectrum analyzer is the instrument of choice. So what is now the spectrum analyzer? Well, a spectrum analyzer, and usually abbreviated with SA or SPA, is a measurement device that measures how much power there is in a frequency interval. And there are in general two types of these spectrum analyzers. The so-called optical spectrum analyzer, it measures how much optical power there is. But in our context, we are more interested in the electrical spectrum analyzer. And in this case, this is a device that is great if you want to analyze noise or other non-periodic motion. And the idea is that you have an electrical signal, say a voltage as a function of time, you put it to the input, and then in this nice fancy device, it will actually measure the amount of power that is at a certain frequency. And there are in general two ways that that can be done. It used to be the case in old-fashioned devices that there was really a filter that was centered at a certain frequency that had a certain width delta F, and then the power was measured that came through that filter. But nowadays, with fast digital electronics, often it is actually a sample of this time-dependent voltage that is being taken and quickly Fourier transformed to actually also find the power at a certain certain frequency. Irrespective of that, there is usually a minimum frequency, typically in the kilohertz range, depending on what kind of device you have, and also a maximum frequency, and that can range up from hundreds of megahertz when you have a relatively cheap device, maybe a few hundred euros, up to 40 gigahertz devices that will cost you a fortune, and you could buy a nice car for the price of a 40 gigahertz spectrum analyzer. So in this case, we see that the spectrum analyzer is great if you want to analyze things like noise or other non-periodic motion. So what does it mean? I already told you that this device, the spectrum analyzer, measures the amount of electrical power in a certain interval delta F. And when we talk about power, we think about amounts of power in milliwatts or in dBm. And in this case, I want to remind you that decibels, dBms, are really units that engineers like a lot. So maybe you've come across it, maybe you have not. And in this case, maybe as a short recall, decibel is something that is a logarithmic scale that relates voltages to voltages. And in this case, it is the 20 times the log 10 of the measured voltage divided by the driving voltage. And that is something that you use very often to describe responses that you measure with a network analyzer. In the case of the spectrum analyzer, we're measuring power. And for power, there's a similar unit called dBm, where the M in this case stands for milliwatt. And the dBm is defined as a 10 log 10 of the power expressed in milliwatts. And in this case, the electrical power is, of course, something that depends on what kind of input impedance there is. And typically, these radio frequency and microwave devices use an input impedance of 50 ohms. And that input impedance allows you to convert between actual power in volts, so actual power in watts or milliwatts, to that in volts or volts squared. So that's also why you often see power in volts squared, although we of course know from the units that power should be in watts and not in volts squared. But when you know the input impedance, almost always 50 ohms, you can always go back and forth between that. And it's usually easier to think about voltages than to think about powers. Well, irrespective of that, the figure to keep in mind is that 13 dBm corresponds to about 1 volt of your measurement device. And of course, in this case, this is now a logarithmic scale. So if you have, say, something that is 10 dB lower than this dBm, you have also square root of 10 lower voltages in this case. Well, that is a short recap of dB and dBm. Of course, we see that the power that you measure also depends on this interval, delta F. And delta F is called the resolution bandwidth of the spectrum analyzer, or RBW. And that's something that you can typically enter on the device, and you can set it to a very small or a very large value. And if you set it to a very small value, then in this case, you will be able to see very narrow features in your spectrum. But that, of course, sounds great, but of course, it also comes at a price. In this case, when you choose a very small resolution bandwidth to see those narrow features, you also are going to have a very long waiting time before your measurement finishes. So in this case, you typically want to select the largest resolution bandwidth to have a quick measurement, but also a relatively small one so that you can still see that. So there's always a balance here. And this balance, of course, also depends on what kind of signal you have. So for example, if you have a signal that is at a very well-defined frequency, then in this case, the power is going to be independent of the interval that we choose. And in this case, you can think of this as driving your harmonic oscillator at a single frequency. And in this case, your spectrum will be a very sharp peak at that frequency. And the amount of power is going to be independent of the delta F that you're choosing. So in contrast, when you now have a broad signal, that is, the signal extends over a broad range of frequencies, then in this case, the power that you're going to measure is going to be proportional to the resolution bandwidth delta F. And the most extreme example here is white noise, where the spectrum is independent of frequency. So it is completely flat. At every frequency, you'll measure the same amount of power, and that power will be proportional to the resolution bandwidth delta F. And in this case, it makes a lot of sense to normalize the amount of power that you measure by the resolution bandwidth. In this case, you get a quantity that is called the power spectral density, or PSD for short, that is usually indicated with the symbol F. And now we have the units that we had before divided by the resolution bandwidth, which is given in hertz. And you get units like volts squared per hertz, or dBm hertz. Or when you take the square root of that, you get volt per square root hertz. And now you can only see why I told before about the sensitivity in a meter or femtometer per square root hertz. That is exactly coming from this power spectral density, but then not for voltages, but then for displacements. And usually we use subscripts in this symbol S to indicate what quantity you're measuring. For example, a voltage V or displacement U. And here you can see a measurement where now using a spectrum analyzer, the spectrum of a harmonic oscillator has been measured. But we'll come back to this measurement in a few seconds. But you can see that in this case it is expressed in picometers squared per hertz. So this is really a spectrum. So that is what I want to tell about the spectrum analyzer. And as I said, this is great if you want to analyze non-periodic motion, if you want to see what the motion is doing, at what frequency it is, and so on. But most of the time, we are not so much interested in knowing the actual displacement of the mechanical system, but we actually want to detect something with it. That could be, for example, the mass that falls onto it, or we can use an AFM cantilever to measure the surface topography of a sample. But in this case, in this context, we can also use it for force sensing. So in this case, you want to detect the force that is, for example, originating from the gravitational waves that we have as our final goal for today. And then in force sensing, the idea is to use the measured displacement that you have coming out of your harmonic oscillator, coming out of your mechanical system, and use that to reconstruct the force that caused it. So in this case, you would try to make an estimator based on the measured time trace that you have to infer what was the input over here. And of course, it makes sense that the better you know the properties of your harmonic oscillator, the better job you can do in estimating the force here. And since this harmonic oscillator is a linear time invariant system, it also means if your force is large, if you have a very large input here, you're also going to get a very large output. In other words, you're going to get a very large displacement. Then if you have a very small force, in this case, you're going to get a very small displacement. And of course, when we have very small displacement, that means it's more difficult to measure this small displacement. And how difficult it is inevitably related to how much noise there is. So that's why we have the relation between sensing and noise. That's why we have been focusing also on, for example, the spectrum analyzer as a method to measure noise. So now the last thing that we can ask ourselves, well, a large force gives us a large displacement, a small force gives us a small displacement. What if there's no force at all? Well, it turns out that even without actively driving the resonator, it is not going to stand completely still. And at very low temperatures, we have always the so-called quantum zero-point motion. And in this case, this is originating from the fact that if you are in the quantum ground state, so here we see the quantum harmonic oscillator, quadratic potential, and you see in black the dotted lines corresponding to the different eigenenergies. You can see the lowest eigenenergy still has finite energy. It's not at the bottom of the potential. And here in orange, you can see the wave function. And this wave function had a finite spread. And that is what is called the zero-point motion. And the zero-point motion is then defined, or the zero-point motion squared is defined as the variance of the expectation of the displacement operator squared if you are in a quantum ground state. And when you do the math, you'll find that's related to h bar and then divided by 2 times the mass times the resonance frequency. So in this case, you can see that if your mechanical resonator is lighter or if it moves at lower frequency, then in this case, the zero-point motion will be larger. So if you look at the device that I showed you earlier, so this is a device that we used to study mechanical squeezing. It is incorporated in a Mach-Zehnder, but when you zoom in, you will see that there is actually a mechanical compliant device that can move in plane. When you calculate with the properties of this device, frequency about 1 megahertz, mass about 500 picogram, you will see that in this case, the zero-point motion is about 3.5 femtometer. So that is really, really small. But still, as I said, sensitivities are typically of the order of femtometers per square root hertz. So it is not so crazy to think about this zero-point motion. However, there is one problem, and that is to actually be in this quantum ground state, you have to cool down these resonators to very, very low temperatures. So for example, for the device that you see in this picture over here, you would have to cool it down to about 40 microkelvin to be in the quantum ground state. And that is, of course, something that is going to be very, very challenging. So in this case, when we are at higher temperatures, and usually we are, of course, then there's also another type of motion, and it's the so-called thermal or Brownian motion. And for the same device, when you calculate how large the amplitudes are in this case, then you'll see that's about 14 picometer at room temperature. So still very small, but about a factor of 4,000 larger than the 0-point motion that you would get. So if we now look back at this measurement that I showed you earlier, where we looked at the spectrum of a harmonic oscillator, then in this case, that was actually the spectrum measured on this kind of device that we have over here. And there's a number of things that we can see in this spectrum. And that is that first of all, there is a flat background indicated by the black dashed line. And this is the noise floor of our detector. And in this case, we'll see later on that we usually call this imprecision. And the imprecision or the sensitivity is about 89 femtometer per square root hertz. So indeed, as I promised you, optomechanical devices typically have sensitivities that are expressed in femtometer per square root hertz. And in this case, I do want to point out that the detector is not so much the physical photo detector that we use to detect the light, but it is actually the combined optomechanical system in its entirety. So this is now the noise floor that tells us how well we can resolve the motion. But what about this other elephant in the room, this huge peak that we see? Well, it turns out that this huge peak is actually this Brownian motion. So you can see that we can really nicely resolve with a signal to noise ratio of about 1000 this thermal motion peak. And look, this thermal motion is only 14 picometer, and we can see very, very clearly this peak standing out over the noise. So you can indeed see that optomechanics is one of the most sensitive ways to measure mechanical motion. So we have, of course, talked already quite a bit about the sensitivity of optomechanics, and we now know that it's very closely related, this topic, to noise. If you have a lot of noise, you have bad sensitivity. If you have very little noise, then you have very good sensitivity. So now we can ask, well, how much noise is there? And in particular, what are now the ultimate limits with which we can detect displacements? And that brings us to the next topic, namely that of quantum limits. So in this case, what we're going to explore in the next part is to look at quantum limits. And we see that we had these three different topics that we're going to address, namely the Heisenberg uncertainty principle, the Hauss-Cave derivation, and the standard quantum limit. However, I think now I've been talking for about an hour or so, so I think it would be good to have a short break. So I think we can have a 5-minute break so that we have time to go to the bathroom, to get a coffee or something else to drink, and then we continue with this exciting topic about quantum limits. So I think we should see each other then at 11:40, and then we continue with part 2, when we're going to dive into the quantum limits on position detection.
Okay, thank you.
Okay.